So look, thus far we've covered a lot of functions, and now I wanted to show you how you can practice all this knowledge that we've obtained, and of course how can you extend it. Now we're gonna use today a DESMOS calculator. Link to this calculator you can find in the description of the video, and I just wanted to show you what can you do with it. Okay, look. So once you're there, it is easy to graph any of the functions that we already covered. For example, let's start the way we started. Y equals to 2. Yeah, you see over here, we're getting a straight horizontal line parallel to x-axis. And look, in this way, you will be able to actually tackle any function. Just you need to write down the formula. Actually, as you see, we don't even need to have, well, if we have x, we don't need to have y. But let's keep it for a while. Okay, what else can you do? Look, you can also observe this function from the further distance, or you can see it in details. And what is important, when you click on the function, it will also show you important points. So here we have y-intercept. Okay, but let's start with so what else can we learn? We learned that if the value is going to be bigger of a constant, we should expect function that lies higher. And look, this is what we get. And we also see new intercept at 3. Okay, but this is not a very interesting case. Maybe let's do some linear functions. So let's just start with function x plus 1. Again, we can read intercepts from that, and now we can see what will, for example, happen to this function if I'm gonna add a different intercept. Look, we see that with bigger intercept, we get exactly the same function, parallel to the one we had before, just this time 3 units higher. Again, from here, you can read the intercept. Okay, now we can see what happens when we change the slope. Look, if I'm gonna put 2 over here, you see that the slope of the new function is higher. This function, as you see, grows faster than this one, and we see this by the fact that it's above the previous one, and the angle of this function is simply higher. And look, by the same token, we see that if the intercept, if the coefficient is lower, we are getting the function that is getting flatter. And look, of course, now we can check what happens if we have negative coefficients. Look, now what we see is that when I go from from the first function to the fourth function, we are actually rotating the function. And when coefficient becomes negative, we see that the function has negative slope. And then we can see it further, that if the absolute value of this negative slope, you see, now I can simply write negative 2x plus 1, right? Because you don't actually need to write 1 over here. And now the function rotated even further. So look, we are starting from 2x, coefficient 2, then we've got coefficient 1, coefficient half, coefficient negative half, and we see that with coefficient negative 2, we are constantly rotating function around 1 clockwise. Let me just show you this. Okay, but of course, we don't need to restrict ourselves to linear functions. Let's now try using quadratic function. Look, if you want to do quadratic function, you use this symbol called hat. you will be able to make it when you press Shift and 6. And look here now. The cursor is appearing in exponent, and I can put here 2, and I give square function x squared. And of course, we see that if I put minus in front, right away, the hands of parabola are going down. But look, let's do one thing we haven't done. Look, what happens when we impose a coefficient on x squared? And look, if I'm gonna here now draw a function y equals 7x squared, look what has happened. This function is increasing faster, right? In both directions. So if you impose a positive coefficient that is higher than 1, you will see that actually the parabola is getting thinner. On the other hand, if I would put a coefficient on y equal to, let's just say 0.3 x squared, you see that this function actually is wider. And look, if I would add here another 0 and another 0, this function is getting wider and wider and wider. Now, of course, we can make a more complicated function, like plus 2x plus 1, right? This is a very simple case, but see, here you can check the tip of the parabola, vertex, and here you get its coordinates, and the same for the intercept. But of course, we can try it here with different functions, and you see you can get from here all the information you get about any transformation to this function. Now let me just copy this, and look, what if I impose minus now on the entire function? Look, we got a mirror reflection of this function with respect to x-axis. You can see it over here. Here we've got 0.06. Here we've got 0.0-6, right, as intercepts. Okay, but we can try, of course, with different functions. Okay, and look, here we've got a case of a parabola that has 2 roots, so it cuts through x-axis in 2 different places. Now, what would happen if I'd like to impose absolute value on this function? We use function ABS, and look, what we see is that now everything on this function has remained the same, while this part, as you see, we've got again mirror reflection with respect to x-axis, because everything that used to be negative becomes positive. Everything that used to be positive stays positive. Okay. Now, one thing we couldn't do thoroughly in class were polynomial and rational functions. Look, here you have an example of a polynomial function. Now, you see that here we've got powers, various powers of x, and you see that we are getting this wavy shape. It has one maximum over here, local, 2 minimums over here, and then the hands of the function, let's just say, call it like that, are going up. But look, if I would, for example, put minus over here, we would see a very different picture. Yeah. So over here, you can very easily observe how different transformations will embark on this and any other actually function. Now here you have an example of of a rational function, as you see, their graphs are even more complicated. But of course, once we will start using calculus, you'll learn that actually even drawing the functions with such complicated graphs is not such a hardsome task. But okay, let's go back to the functions that we dealt with. And the next one is going to be 1 over x. Okay, this is the function I think, we've seen the most times. Now, let's see how all the transformations that we've encountered here work. Okay, let me copy this function over here. And now, the first transformation that we can do is, for example, to add 2 to this function. And look, we get a function that is 2 units higher. But we should also remember about asymptote. How can we make asymptote? For example, y equals 2. This is the asymptote here. So you see that the value of the moved functions are getting closer and closer to this asymptote, but never reach it, right? Now, what if I want to make this function even more complicated? And now I want to subtract something from x. You see that now function moved to the right. Again, we can use an asymptote. This time, remember, it's going to be x equals to 1. This is not a function, but we can use this formulation as an asymptote. And again, as you see, we can actually check all the points. What else can we do with this function? Well, we, for example, can take it and put absolute value on it. Okay, how will this look like? You see, everything that used to be positive just remained the same. Okay, let me just make the picture a little bit more clear. As you see, the same asymptotes are sufficing. Wait. Oh, sorry. Wrong function. And now we got a slightly more complex shape. Let's compare it with the previous one. You see, only this part was below 0. So only this part was changed and moved over here. And look, now if I, for example, add here minus, everything that used to be above goes below. And now we can also do something like compare the function 1 over x with the function 1 over x squared. So you see that this is exactly what we said during the lecture. That here you've got a 1 over x function, the purple one, and now what happened? The red one. Once we add square, the slope of the function changes. The function is becoming steeper, and we see also that this part goes over here and changes the slope. Well, I encourage you to do as many transformations as you can and see what happens. It's gonna stay in your head, and look, those functions that we've covered, you will see them in economics, in econometrics, popping up all the time. So it's good that you would be familiarized with these functions. Okay, so let's move to the next one. Let's try e to the power of x. This is natural exponential function. We see here 0.10, and we said last time that this function is getting closer as we go to negative infinity. So over here, it's getting closer and closer to 0. And look, we can see this easily if I, for example, add 2 over here, right? you will be able to see, okay, actually, let's start without it. Let's use the option that we can actually magnify the graph. Look, how does it work? The function gets closer and closer to 0. And look, even if we think it's already at 0, like here, if I'm going to magnify it further, we see that there is a space between them. But it also means that we can, for example, add 2 to our function, and it's 2 units higher. You see now the intercept is a 3. And if I'm going to put now y equals 2, you see we created an asymptote. And again, if I'm going to be magnifying this, those two never coincide with each other. Okay, now let's see a couple of interesting transformations we can do with this function. For example, what if I'm going to put minus here? Well, the function, actually it's better to see them both. E to the power negative x. We see that the two are mirror reflections of one another. But of course, there are other interesting things we could do. Like, for example, I could put absolute value on x, right? And look what happened to the function. This part stayed the same, and this part went up. Because remember, when I impose absolute value on x within the function, I get mirror reflection of what is on the right hand side on the left hand side of the vertical axis. Okay, and look, we can do way more with this. For example, if I now put minus over here, look what has happened to the values of this function. Because now we basically have okay, let's see, e equals y equals e to the power negative x, right? Look, now we've got this shape over here and over here. Well, you know, the most famous transformation of e function is when you do something like this. You take e to the power negative 0.5 x squared. Now, what you see over here is a function that gives us something that is called normal distribution. This normal distribution actually is used very often in statistics, and you will be discussing it very well. But as you see, we are obtaining it from the simple function e to the power of x, but simply by adding some additional transformations. Okay, I think that's enough about e. Maybe just one more thing. Oh, look. Okay. Okay. Now, y equals natural logarithm of x. And look, we said that those two functions are mirror reflections of one another with respect to y equals x. Y equals x line. And I hope you can see this way better right now, right? We clearly see that the distances between the two functions and the mirror in form of y equals x are exactly the same. And look, if I'm going to use now minus x and logarithm log with Okay, with base 1 over e. I'm sorry, wait, with base. Okay, I don't know how they figure out logarithms here, but it doesn't matter. Okay, we saw this one. So the next, finally, the functions we've covered at the end are the trigonometric functions. So we've got y equals sine x. Right. Now, what can I do with it? We consider a couple of transformations. Like first, let's consider y equals 3 sine x. And so let's see what happened. We can use asymptotes. Okay, let's go back to the initial function, right? We expect to have the highest value of this function is 1. So let's start with this. And the lowest value this function can take is -1. Now, what happens if I'm having function sine 3 sine x? Well, now we expect that this function will have highest value at 3, and you see this over here as well as here, at the same point where our previous function had 1, and it has 0 value because 0 multiplied by 3 is still 0 at the intercept. And look, if I would change now this to 3, this to -3, you see that we've got those values over here. Okay, another transformation that we've discussed is what if we impose a number that is between 0 and 1. Look, now everything, the sinusoid has become flatter. Now the range of values goes from 0.5 to -0.5. Okay. What else? But now let's try some of the things we haven't done during the class. What if I would have a function minus x minus sine x? Look, the interesting thing that happens over here is that what used to be positive becomes negative. What used to be negative becomes positive. Yeah, we've got mirror reflection with respect to x axis. Oh, now we can try also what would happen if I impose absolute value. And what do we see now? What used to be positive stays positive. What used to be negative is now positive. So as you see, everything works. All the transformation that I've told you about work the same with every function. And now let's see one more thing. What if I impose absolute value? Oh, I'm sorry. I should have done it. We are missing one. We are missing one. We were missing one parenthesis. Okay, and now look what has happened. This part of the function stayed the same, but now you see its mirror reflection going in the opposite direction. Okay, so second function we've done from trigonometric function is cosine. Okay, and you see that basically sine is cosine moved a little bit. By how much? Oh, let me see if here the trick with pi would work. It works. Okay, so here we have cosine function. Here we have sine function. Okay, and look, what I wanted to do is to move cosine in such a way that it will be equal to sine. By how much do I need to move it? Well, definitely it will be something associated with pi. But look, when I added pi, we moved too much. So maybe it should be pi over 2. Well, we clearly see that this trick doesn't work. But we remember one more thing. If I want to move a function to the right, I should not be adding, I should be subtracting. And look, exactly this is what happens. If I moved cosine by 2, you see, by the pi over 2, you see, I'm getting sine. And the same would be with sine. If I take the sine and add pi over 2, in order to get pi, you just write pi, pi. What am I obtaining? Cosine. Okay, now, the next transformation we were doing is what when you impose a number inside, a coefficient inside the function. Oh, I'm sorry. Oh, here I'm missing y. Equals. And look, you see that now the function increased in speed twice, right? Before, in order to do 1 for circle, it requires 2 pi. Now it just requires 1 pi. And by the same token, if I would put here number between 0 and 1, like half, you see that now the function spread it out and it takes it twice as much time to do the full circle. Okay, then we had tangent. Tangent. Okay, and tangent looks like this. Okay, we don't need cosine. Okay, let's make it a little bigger. And now, what do we see over here? Well, we expect to have some asymptotes, right? At x equal to pi over 2. And we do have one. Where would we have another one? For example, at x equal negative pi over 2. Then we would have the next one at x equals negative 3 pi over 2. And the next, and as you see, we will have we need to have additional asymptote on each product of pi pi to k plus k pi, right? And finally, the last function is cotangent. Give me a second. Ctn. Cotangent. Okay. Now we need to fix our asymptotes because they are going through the function. So where should they be now? Well, I think this one probably should be at pi, and this one at 0. And yeah, this is what we see. Okay, and look, within this program, you can make as many transformations as you want. I can impose now number, so we will obtain more cotangent function. I can make it less steep by putting a coefficient on it. But look, the most interesting thing about cosine trigonometric function is what happens when you combine them. Look, if I'm going to take function like sine x plus 3 cosine x, minus 2 sine 0.5 x, 0.5x plus 0.5, let's just say cosine 4x. Look, what you see over here is that we are getting a function that is still cyclical, but is becoming more and more and more complicated. And this is the real power of trigonometric functions. Look, economy, so GDP of a country is cyclical to some extent. And because of that, we can make a model of it using trigonometric functions. And we will actually learn how to do such things, but in the future. Okay, I think this is enough, but I would really like to ask you to try to work with this graphical calculator, because it will answer you all the questions you need. And remember, on the first test, you will have to draw a lot of functions and do it properly with all the intercept and everything using transformations that we learned. I believe this is a great tool that can help you learn all of this. Okay, thank you for your attention and see you in the next video.